Good morning, champ. Today we're taking on our first nonlinear differential equation. Don't worry, we're not diving into chaos just yet. We're focusing on a special type that looks nonlinear, but can be tamed with a clever trick, the Bernoulli Differential Equation. These equations pop up in models like population dynamics, chemical reactions, and even fluid flow. And the best part? With one smart substitution, we can turn them back into a linear equation. A Bernoulli differential equation has the form y prime plus p of x times y equals q of x times y to the n. At first glance, that y to the n term makes it nonlinear, but if n equals 0 or n equals 1, the equation is already linear, so the real challenge and the fun starts when n is not 0 and not 1. Let's make it linear again. We start with y prime plus p of x times y equals q of x times y to the n. Divide both sides by y to the n, and we get y to the negative n times y prime plus p of x times y to the 1 minus n equals q of x. Now we introduce a new variable that simplifies things beautifully. The goal is to eliminate that messy power of y, the part that makes the equation nonlinear, and transform everything into a form we already know how to solve. We start with the term y to the 1 minus n. This is a smart choice because it directly cancels the powers of y in the equation when we divide by y to the n. So let's define a new variable. V equals y to the 1 minus n. Now, to understand how v changes as x changes, we need its derivative with respect to x. Differentiate both sides using the chain rule. Dv over dx equals 1 minus n times y to the negative n times y prime. When we differentiate I to the 1 minus n, we bring down the exponent 1 minus n, and then we multiply by the derivative of the inside, which is y prime. The power of y decreases by 1, so we get y to the negative n instead of y to the 1 minus n. That's why the derivative of y to the 1 minus n is 1 minus n times y to the negative n times y prime. If you look back at our Bernoulli equation, we already have a term y to the negative n times y prime sitting there. That's the key connection. This new variable v lets us express that messy nonlinear term as something involving just dv over dx. We can now solve this expression for y to the negative n times y prime. It becomes y to the negative n times y prime equals 1 over 1 minus n times dv over dx. This is the magic moment. That single substitution untangles the nonlinear power of y. We've replaced the nonlinear mix of y and y prime with a single linear derivative of v. When we plug this back into our differential equation, everything collapses nicely into 1 over 1 minus n times dv over dx plus p of x times v equals q of x. Multiply through by 1 minus n to clean things up, and we get dv over dx plus 1 minus n times p of x times v equals 1 minus n times q of x. And there it is, a linear first-order differential equation in v. From here, it's back to our familiar world. Find the integrating factor, integrate both sides, and then substitute back for y. Let's work through a concrete example step by step. We'll solve y prime plus y equals e to the x times y squared. Here p of x equals 1, q of x equals e to the x, and n equals 2. Step 1, divide through by y squared. That gives y prime over y squared plus 1 over y equals e to the x. Step 2, substitution. Let v equal 1 over y, which is y to the power of negative 1. Then dv over dx equals negative 1 over y squared times y prime. Rearranging gives y prime over y squared equals negative dv over dx. Substitute this into the equation. Negative dv over dx plus v equals e to the x. Step 3, simplify. Multiply through by negative 1 to make the derivative positive. dv over dx minus v equals negative e to the x. Now we've got a linear first-order equation in v. Let's find the integrating factor. The coefficient of v p of x equals negative 1. The integrating factor mu of x equals e to the integral of p of x dx, which is e to the integral of -1 dx, or e to the negative x. Now, multiplying through by e to the negative x gives e to the negative x times dv over dx minus v times e to the negative x equals -1. The left-hand side is the derivative of e to the negative x times v. You can check that using the product rule. It's a perfect match. So the whole equation becomes d over dx of e to the negative x times v equals -1. Now we integrate both sides with respect to x. The integral of the left-hand side gives e to the negative x times v. The integral of the right-hand side gives -x plus c. That gives us e to the negative x times v equals -x plus c. Multiply through by e to the x to isolate v. That gives v equals e to the x times -x plus c, or equivalently, v equals e to the x times c minus x. Now remember, v equals 1 over y. Substituting back, we get 1 over y equals e to the x times c minus x. Finally, take the reciprocal to find y. Y of x equals e to the negative x over c minus x. And that's your general solution. Now let's take a step back and see what we really did here. The Bernoulli equation may start nonlinear, but it only takes one clever substitution, v equals y to the 1 minus n, to drop it right back into the linear world. This is more than a trick. It's a deep insight. It shows that many nonlinear systems can be linearized if you know how to look at them from the right perspective. By defining v as y to the 1 minus n, we transform the nonlinear behavior into a linear one, turning a difficult equation into something we can handle with the integrating factor method. So champ, here's your summary strategy for any Bernoulli equation. Step 1, start with y prime plus p of x times y equals q of x times y to the n. Step 2, divide through by y to the power of n. Step 3, let v equal y to the 1 minus n. Step 4, rewrite the equation in terms of v. Step 5, solve the linear O, dE for v using an integrating factor. Step 6, back substitute to find y. And that's it. The Bernoulli equation looks nonlinear, but with one elegant transformation, it behaves just like a linear one. So champ, the Bernoulli equation is your first taste of nonlinear magic. It starts messy, but with one clever substitution, it snaps back into linear form. All right, champ, keep that pencil sharp and that coffee strong. You're bending nonlinear math to your will.